I'm not gonna be a person to rush somebody into being super good. So I said everything in front of you. If you don't want me to do that, tell me now. But you have control of the meetings in front of people. Because I feel like it would be more frustrating for you to not be able to more frustrating than doing it.
What's this the? Oh, I think it's great on the next page.
Yeah, it's on the inside page.
Yeah, it's on page 3. Oh, chapter 600. Oh, and chapter 7. Right there. Thank you. On the test? Or on the lab? Yes. This one? This one got me so confused. Yeah, what's your list, by the way? Oh, you divided. Yeah, I think that was probably on the last page I did, no, not the last page. Yeah, on the last page I did. Oh yeah, see it was UV. You were right on that one. With violet.
So maybe 19 is supposed to be -18. I just like multiplied wrong or something. No, I read the number wrong.
Oh, on the last one? I completely messed
I
up.
about fell over.
I mean, you just missed the exponent though.
True.
Yeah, it was lovely. Did you put like a positive number or something?
No, I don't.
Did you get a negative or positive? You got negative. You probably plugged in like another negative.
Yeah, I must have done something wrong with my calculator. So.
You got that part.
Like, I got the equation right, but not the answer.
There was a lot of that on that back page. It's like people set it up all correct and then driving me crazy with that lack of mental math.
It's like the exponents. If you like put a plus or minus on the exponents on top in the answer, you get like the wrong one. So that's basically it. I think I like put a plus on one of these, like put 9 or something. So.
What?
It's already happening.
Oh.
No.
Oh, you printed
So
it.
in the post-op questions I was trying to do them last night, and it talks about like there are steps where you can add, where you can like, I forget how it works it, but like you can accumulate additional copper in this stuff. Or the.
Yes.
What is it? Is that the one we just took or what?
Yeah, that was the one we just took
Choose out copper.
on Tuesday.
Is there a quiz today?
Yeah,
Number 5, or chapter 5.
it'll be over like the quantum stuff.
Sweet.
I need to look at
All right, let's go ahead and get started. So double check your midterms. So if you didn't get your midterm, I'll catch you at the end of class, or you can come bother me at the end of class if you snuck in. But double check that I did all the addition correctly. And if I gave you too many points, then, you know, free points. But if something doesn't add up properly and you're missing points, just let me know and I can fix that. And so I'm wearing my bright orange shirt today, not only because it's Halloween on Monday, but registration starts soon. So don't forget to register. So I'm aware that there's like conflicts right now with Calc 1 and 2. So I'm thinking our new tentative time for Chem 222 is going to be, now I forgot if I said 11:30 to 1, I believe. Does anyone know if they have conflicts with that time by any chance? Yeah, I'm trying to avoid all the conflicts. So right now I'm looking at the time 11:30 to 1 for lecture. And then we'd still have to play around with recitation because that looks like that would have to be Thursday 1 to 1:50. And then the lab is still kind of left on whether it's going to be Tuesday after lecture or Thursday after lecture. But I wanted to poll y'all and let me know if there are conflicts. So are there conflicts with this time?
Is it still gonna be on Tuesday and Thursday?
That's my plan, yeah. So it'd be Tuesday and Thursday. Because I'm trying to line it up with the math and the science and coordinate, but I don't know, like, everyone's schedule. So does it seem like a good time? All right, so hopefully this will go through. And so register, expect this to change. So right now it's set to 8:30, but then I heard that there are Calc 2 conflicts. So I'm trying to avoid Calc 1 and Calc 2 conflicts. So hopefully this will be a good time. Let's see, any other things? Any other questions, comments, concerns? And I don't normally do this, but I think Dorothy on Grants Pass is offering a midterm retake. And so I think we're offering midterm retakes, but you'll only be able to get a max of either a 70. So if you got below a 70, you can talk to me personally about potentially doing a retake. But overall, I was fairly pleased with the grades. Most people did really well, so I'm pretty happy with that. All right, other questions, comments, concerns? So let's dive into Chapter 7 then. So Chapter 7 is now covalent bonds. So we did ionic compounds Tuesday, now we're doing covalent compounds today. And so we kind of hinted at this on Tuesday. And so remember we said ionic compounds, they don't have a physical bond, so they're just held together by those electrostatic charges. But now covalent bonds do share electrons. And so we say that electrons that are shared by atoms are called the bonding pairs. And so if we were to draw out water here as our example, and we'll go into, well, how did we even get here in the first place? But we're looking at water. And so oxygen brings 2 electrons. So 1 electron in each bond. So we can start with our Lewis dot structure of oxygen. So these are going to form a bond. We know each hydrogen brings 1 electron to the bond. I'll draw this in another form. So this is just so we can see where the electrons came from. So H. And so again, here's our bonding pair. So 2 electrons in each bond. So anytime we have our line, that's showing that that's 2 electrons there. And then so we look at our water structure. So we have these lone pairs. And so these are electrons that are not shared by atoms, but simply belong to a particular atom. So in this case, they belong to oxygen. And so they are called either lone pairs. So we would say oxygen has 2 lone pairs. So each of those pairs, of course, has 2 electrons, so 4 electrons total. And you could also call them non-bonding pairs. And so here's just another representation. So again, normally we would put a line there to show that they are bonding. So now let's look at the diatomics. And so now we can kind of explain, well, why the diatomics are the diatomics. So if we start with simple hydrogen. So hydrogen just has 1 valence electron, and obviously it's not satisfied by the octet rule, so it wouldn't just hang out like this. And so what we find is that 2 hydrogens come together, and they form a bond here, so we have a single bond in this case. And so fluorine, chlorine, and iodine are all very similar. So of course fluorine now has 7 valence electrons. So if we put 2 of them together, we see they just have 1 lone electron here. And so now this is telling us, okay, they probably want to form a bond, and indeed that is what happens in their elemental form. Like that. And so let's kind of look, so the other thing that you want to do is start to recognize patterns and start to recognize, well, how many bonds do these tend to form? And so if we look, so hydrogen, just 1 electron, satisfied by the duet rule. So this means that it only makes 1 bond. And this is typically, so you may find, if you go on to higher orders of chemistry, like inorganic chemistry, you could find actually hydrogen in some weird bonding scenarios. But just for our case, normal covalent compounds, hydrogen only expected to make 1 bond. And again, it only has 1 little electron. That's all it can do. And so similarly, like we just saw with fluorine, it can also only make 1 bond. So it has all these other electrons. We may find some exceptions where it does some hypervalency and makes some cool compounds, but for the most part, if you see a halogen, right, it tends to only make 1 bond. And then so notice that the entire group then would follow that same pattern. So chlorine, bromine, iodine. And so this is where those patterns start to come into play. So chlorine, again, same Lewis dot structure. So this will only form 1 bond. Iodine, same thing, tends to only form 1 bond. Bromine, same scenario. And so with those halogens, again, we expect them to make their bonds. That's why they're all diatomic. So chlorine, bromine, all the same. And so we'll go back and forth to here as we kind of build our molecules. And so now we might ask ourselves, well, first of all, how do we even predict the type of bond? And I will say, like, trying to predict this type of bond, you would ultimately have to examine this compound in the gas state, do various experiments, and see, is it really ionic, is it really covalent, what is it? Well, this is a good general trend. And so what we have here are the electronegativity values. And so do we remember electron affinity from Tuesday? We mentioned electron affinity, electronegativity. Is that, okay, see some nods. And so now this is just the actual value. So we had mentioned that the general trend for electronegativity and electron affinity, as it increases as you go across and as you go up. So of course these have orbitals that are closer to the nucleus, so they really want to have those shells filled. And so now we see what I was saying with the discrepancy as well between fluorine and chlorine with electron affinity and electron negativity. And again, that's because it's in a bond. And so fluorine is the most electronegative. You often see it rounded to a value of 4. This chart gives a more precise number of 3.98. And so now the question is, well, how do we predict this type of bond? And so what you can do is take these electronegativity values and you find the difference between them. And then that tells you roughly, is it polar, nonpolar, or even ionic? And so again, this is just kind of a general guide. You would have to examine the bonding more in depth and do, again, experiments to see is this really the case. But looking at this general guide, so if you have a small difference in electronegativity, this gives you either a purely covalent or sometimes called nonpolar covalent. So nonpolar covalent bond. And so if we look at chlorine, in our example here, so chlorine, right, we normally think of that, it's a really electronegative element. However, if it's bonded with itself, there's no difference in electronegativity, so 3.16 minus itself gives us 0. And all that's telling us, if we were to graph or do computational chemistry and it spits out what do the orbitals look like, where are the electrons, we would find that they are shared equally. So you have a nice, even, pure, nonpolar covalent bond like this. And so no chlorine, right, is able to pull the electron density from the other since they have the same electronegativity. So as we move across this spectrum and we move towards polar, now we start having uneven sharing of electrons. And generally, once you get above 0.4 difference in electronegativity, that's considered polar, let me see, polar bond. So if we look at our example of HCl here, let's go ahead and calculate it. And so in an exam, you would have to be given this chart or given some values. And so we can look, so chlorine is 3.16, oops. I didn't fire up my calculator. So 3.16 minus, so hydrogen is 2.1. And so that gives us 1.06. And so if we look 1.06, that's right in the middle here. So that tells us it's a polar covalent. And so now this is telling us we have some sort of uneven sharing. And so your atom with the highest electronegativity value, that's the one that's stripping electron density from the other atom. So in this case, right, chlorine is taking that electron density and pulling it towards it. And so this is where we get, again, those partial charges here. So now we can say we have a partial negative charge, and that would be centered around the chlorine. And meanwhile, hydrogen, it only had one electron to begin with. Now it's getting stripped away and pulled towards the chlorine, and so that leaves hydrogen with that partial positive charge. And so again, that's why if you were to dissolve now HCl in water, so it's always acid into water is what you ought to do. And so why is that? It's extremely exothermic, and because it's polar, once it meets water, it's going to disassociate, just like we saw with the salt water. So same effect, so this HCl would disassociate. And so that energetics, that's very favorable for it to dissolve. And so that's why it heats up. You get that exothermic reaction as that's energetically favorable. Yeah.
How do you know which atom to put first in your calculation?
Oh, it doesn't. It should be the greater one first. But yeah, you care more about like the absolute value of the difference. And then so as we go across, and again, this is just a general guide. You may find, if you were to do research, you can always find bonding exceptions and weird scenarios, but just in general, once we get larger than 2.0 in difference, now that's considered an ionic bond, so they're completely separate and no more sharing of electrons. And so let's calculate that for our sodium chloride example. And so let's do, so there's chlorine again, 3.16 minus sodium, so 0.93. So that gives us 2.23. And so that tells us it's ionic. And then we know it's ionic from its properties, just seeing it light up the light bulb. So there's our hint. Now let's look at kind of formally how to define all these types of bonds. So we've just been looking at our single covalent bonds initially, especially with our diatomics. And so anytime you see a covalent bond, usually it's just a single bond unless it's specified double, triple. And so again, those single covalent bond are just sharing 2 electrons. And so, of course, you can use more than one single bond to fulfill its octet. Again, we'll go through the patterns so we know right away how many bonds it wants to make. And again, hydrogen is satisfied by the duet rule, so it only needs 1 bond. And so now let's look at our other diatomics. And so looking at oxygen, its Lewis dot structure, how many bonds do we think oxygen wants to make? So 2. And so we see this, and this holds true now for our group 6. We'll see this pattern repeated. So group 6, they all have that general 2 lone pairs and then 2 lone electrons. And so excellent job in recognizing, okay, those 2 little lone pairs means that they like to make 2 bonds. And so again, this is just in general what they like to do. And so sulfur does the same thing, selenium, just go down that whole row, tellurium, polonium, so they all tend to make 2 bonds. And so if we go back to then our diatomic, if we're thinking about how it could bond with itself, so what do you predict then for O2? Yeah, and then how many bonds then? So it has to be a double bond. And there's a couple of different ways to get there. So I get there right away because I've been doing chemistry a long time. I look at oxygen. I know it's going to make 2 bonds. And so if it's bonding with itself, it likely makes 2 bonds. But you don't have to get there right away. And so kind of the trick in how to approach these is first you ask, what's my total number of valence electrons? And so if we're looking at O2, right, each oxygen is bringing 6 times 2 is 12 electrons total. Now there's a bunch of formulas and crap you can do to try to determine the number of bonds, but sometimes it's not always that helpful. So what you can just do is just start literally putting electrons around and seeing what happens. So you know you need to get to 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so then we could see, well, what's kind of wrong with this structure? So what's wrong with this structure?
The second lecture has an empty orbital.
Yeah, so this guy doesn't have an octet, so it's pretty sad. And we'll look at other ways to analyze it by formal charges. But this is your hint. So step 1 is usually you want to satisfy the octet rule. So right now they're not satisfied. And so that's where I would try other ways to draw it. And so you can't really add other electrons, right? We can't just add 2 more. Now we have 14. That's too many, so we can't bring that to the party. And so in this case, we could see, well, if I just shift these over to a double bond, maybe that would help. And so this is where, guessing and checking is totally appropriate. And so now, let me try that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now I have my 12 electrons, and the octet rule is satisfied. So 1, 2, 3, 4, 5, 6, 7, 8. And then my other one, 1, 2, 3, 4, 5, 6, 7, 8. And so now we'll look at it. So this is called a double covalent bond, or just a double bond. And so now we're just saying they're sharing 4 electrons total, so 2 bonding pairs. And so other elements that can double bond with each other or themselves are going to be carbon, nitrogen, oxygen, sulfur, and phosphorus. And so we'll look at funny scenarios, but phosphorus can make compounds like that. So some sort of R group could be carbon, hydrogen, and then double bonded to oxygen. Carbon tends to double bond with itself. It can also triple bond with itself. So same thing with oxygen. Sulfur would do the same thing. And so now if we move over to nitrogen, so how many bonds would it have in diatomic N2? What do we think? So 3, exactly. And you can tell that, well, it's got 3 lone electrons. So that's a good hint. You could also count up how many electrons you have in the party. So each nitrogen, so how many valence electrons does a nitrogen atom have? So 5, there's 2 of them, so 5 times 2 gives us 10 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Octet rule is satisfied, 1, 2, 3, 4, 5, 6, 7, 8. And symmetrical, so same thing on the other side. And so now add this to your trends as well. So now we're kind of seeing in general for our simple compounds, and we'll go over other trends. So group 5, they all have this structure. So phosphorus, same thing. And so we've seen that they like to make 3 bonds. And so we can think of other compounds that follow that same pattern. So ammonia, you know right away. Okay, that's going to be 3 bonds. PCl3, same thing. So tend to make 3 bonds. And again, we mentioned carbon. So carbon can triple bond with itself. Then it would need to be bonded to a hydrogen. This is ethylene. And so now we have our triple covalent bond or just a triple bond. And so that means they're sharing 6 electrons or 3 bonding pairs. And so again, these elements can triple bond with each other, carbon, nitrogen, oxygen, sulfur. So let's start, actually I'm going to add an example because I wanted to talk about this molecule. Then now let's look, well, how do we, again, continue to make these Lewis structures and draw in the geometry? How do we predict the geometry? And then what do we do with that? So your book also made a funny comment. So I don't know if anyone read the book, but it says some comment that silicon tetrachloride is used as a smoke screen. And it just said it in passing. And I wanted to point out that it's not like the Halloween smoke screen, so you would not want to use this in a haunted house or something. So that would be used for smoke screen and chemical warfare. So let me pull up a video. Hang on. And so it takes a lot more energy. Yeah, I mean, they have to be careful when they make things like, oh, it can be used as a smoke screen. It's like so can carbon dioxide, but they're completely different smoke screens. So if you want to do a haunted house smoke screen, definitely use carbon dioxide, dry ice. Even that can be dangerous, sorry. Where's my YouTube link? So this is an example of a smoke screen. I don't think there's sound on this video. Come on. Go. Why is this not playing? There we go. So that is a chemical smoke screen. Yeah, so that is pretty nasty. So from this video, I wasn't quite 100% sure which chemical they were using, but it's one of 2. So that is pretty scary.
So what happens when that combines with the salt water?
So it more reacts with the atmosphere. So what happens, so if you have silicon tetrachloride, or the other thing that was used in there, which again I'm not sure, it's either silicon tetrachloride or titanium tetrachloride. This is affectionately called tickle. It's affectionately called this way because it's pretty nasty. So what happens is these compounds react instantly with the water in the atmosphere. And so they both react with H2O. So that's what's doing. So it's dropping whatever the pure chemical is, either silicon tetrachloride or titanium tetrachloride. And so that makes either titanium dioxide, which gives you that smoke screen effect, or silicon dioxide, which would do the same thing. But then you also form lovely HCl gas. And so this is why I was not very happy that your book just was in passing, like, yeah, it's a smoke screen. You'd be breathing in toxic HCl gas, and that's why it was obviously used in chemical warfare, because not only do you blind everybody with a nice smoke screen, but then you can, choke them out with a little bit of HCl gas. So tons of fun there. And so both of these compounds are fairly reactive and nasty because of that. And so tickle, chemists call it tickle since, again, it reacts instantly. This is also called a glove box killer because it is so reactive and it makes HCl, and HCl is horrible for a glove box if you're trying to keep a water-free, air-free environment. So if you were ever working in a glove box, your mates would not like you if you opened up Tickle. And so now let's look at how we can draw our Lewis dot structure of, we'll do silicon tetrachloride, although titanium is actually just the same. And so I would start by adding, so how many electrons are coming to our party? So how many does silicon bring? Or how many valence electrons? So 4 valence electrons. And then how many does each chlorine bring? So 7. That gives us 28. So 28 plus 4 is 32 electrons. And so this is where it's kind of helpful to know your patterns. So looking at silicon. So silicon is part of group 4. And so we mentioned that silicon can either be this divalent compound, so it can be stabilized like this, although not that readily, so it's still pretty unstable. But we also find, so our group 4 tend to make 4 bonds, like we've seen with methane. So methane. And so now looking at this without even knowing anything, so you could just kind of surmise, well, I have silicon. It can make 4 bonds. Each one of these chlorines, right, can only make 1 bond. So it kind of makes the most sense. Just stick silicon in the center. Make your 4 bonds to each chlorine. And then tally up your electrons. Make sure that your accounting works out. And so we have 32, so I want to put 8 on each one. So I just have to fill in my 6. And so this looks good, and we have 8 times 4, so that gives us 32 total electrons. And then just for, this will come up later, but we'll introduce it. So this would be tetrahedral for the geometry. Start practicing. And so now let's try OF2. And so take a few minutes, see if you can figure out what would be the structure for OF2. And we'll go over how to analyze it. Did everybody get their exam back? I think that caught everybody. So have we gotten a structure for OF2? Does this remind you of some compound? So what's the simplest way to draw this? Sorry? So O in the middle, and so probably just make one bond to each. And so to me this looks like water, that's what I was trying to get at. So it's the same thing, right? We just replace hydrogens with fluorines. And so to me, just looking at this, this makes logically the most sense. As soon as you see that oxygen, you're thinking ding, 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 only 2 bonds. Each fluorine, though, can only make 1. So this seems to make the most sense. But I wanted to go over, because your book makes a point of this, is let's say you didn't know that oxygen was in the center. How could you determine that this was indeed the better structure than doing some sort of fluorine oxygen bond? And I don't even know if I can make a structure. So let me see how many electrons we have, since that's where we should always start. So 7 times 2, so 14. So it looks like we have 20 electrons. And so just trying to fill this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that makes some sort of structure. And so this might seem okay. Our octet rule looks satisfied, but we have to look at another factor. And so the other way to analyze your structure is this thing called formal charge. And so it's basically related to the valence electrons. And so the formula is this. So your formal charge is equal to, so the total number of valence electrons. So this is just from your periodic table, right? What group is it in? Okay, that's my valence electrons. And then minus the total number of lone pair electrons, or sometimes I just put like total electrons. So that means for this fluorine, it would be bonded to 1, 2, 3, 4, 5, 6 individual electrons, and we'll do the formal charge for each of these in a second. And then minus, they say half the total number of shared electrons, but sometimes I just say minus the number of bonds. So that would give you the same number. That's just easier to me to count lines as opposed to double them and half them. And so now let's calculate the formal charge. We'll do it for our nice structure first, and then we'll compare with our theoretical one and see if that tells us which is better. So if we go back to what we assume is kind of the correct structure, since it matches well with our patterns. So I'm just going to call this F1. So for the fluorine, we start, so 7 valence electrons minus, so it's bonded to 1, 2, 3, 4, 5, 6 lone electrons minus 1. So that gives me 0. F2 is the same thing, right? It's symmetrical, so 7 valence electrons minus 6 lone electrons minus 1 bond, so that's 0. Then our oxygen, so we have 6 valence electrons in oxygen minus 1, 2, 3, 4 electrons minus 1, 2 bonds, so that's 0. And so that's good. And then, so the other rule about formal charges is formal charges have to add up to equal the charge of your molecule. So in this case, we're just looking at neutrals, so they should all add up to 0, but later on we'll do charged compounds, and so that will matter. And you'll have to put the formal charge where it's located. And so now let's compare. So help me with this one. What's the formal charge then for this structure? So let's start with, we'll call this F1, F2. So F1, so walk me through. So what's the first thing? So we do, so 7 minus how many electrons? How many bonds? So that's 0. Let's try, so F2. So 7 valence electrons minus, so how many lone electrons? So 4, how many bonds? And so what's that formal charge? So 1, and so oxygen would be 6, and then minus how many electrons? And how many bonds? So what does that give us? And so, here's our red flag. And so the next rule for formal charges, so we want to minimize formal charges. So we don't want them, but sometimes they can't be avoided. But the other thing is, so the most negative formal charge should be on your most electronegative element. And right now we're carrying a +1 charge on fluorine and a -1 charge on oxygen. So that really doesn't make sense. So fluorine's the most electronegative, so it would want to be taking those electrons for oxygen. So it wouldn't make sense that oxygen is carrying that negative charge. And so from here, this is telling us maybe not the best structure. And so in this case, you could conclude, well, this is probably the shape of OF2 just based on our formal charges and the octet rule. But I'm trying to give you advanced knowledge too, where you just look at it and say, yeah, it has to look like that. That's what makes sense. It wants to make 2 bonds with oxygen, and fluorine is only going to make 1. And so not saying that fluorine can't be in the middle, so there's a compound called II3. So fluorine probably wouldn't do that, but the halogens can be hypervalent. But fluorine is just too physically small to be hypervalent. So let's practice. See if you can figure out C2H4. So just start with how many electrons do you have in the party? What are the possibilities? We need double bonds, triple, single. So what should our structure look like?
Would the carbons be next to each other with a double bond? And then for the remaining 2 electrons for each carbon, 1 hydrogen would be bonded to each.
That is excellent. So what's kind of the easiest way to get here? Because if you started off, you could just put 1 bond to each. Then you would see you're like missing electrons in an octet. You also know that carbon wants to make 4 bonds, so that's kind of what you're looking at right away. How can I make 4 bonds with carbon? You could also have tallied up your electrons, so I would always do that just to make sure. So we have carbon, 4 times 2 is 8. And then the hydrogen each brings 1, so 12 electrons. So you know whatever you draw, you have to have 12 electrons in our system. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then this makes sense that our hydrogens should be terminal. So again, I wouldn't expect any bridging hydrogen scenarios in the compounds we look at. And then the other thing, so get used to doing formal charges, at least in your head. If nothing else, do a quick check. So I wouldn't expect there to be formal charges. It's a neutral compound. But just run through. So carbon, 4 valence electrons, minus 4, okay, that's 0. Hydrogen, 1 valence electron, minus 1 bond, okay, 0. And so you don't need to write anything if we have 0 for our formal charges. So try carbon tetrachloride. So see if you can recognize what that looks like, what family it's under. Bless you. So do we have a structure for carbon tetrachloride? Does it remind you of something?
Reminds me of silicon tetrachloride.
So it's just like silicon tetrachloride. You could also throw in there methane, so all the same. And so we should have something that looks just like that. And so fun fact, so carbon tetrachloride is pretty carcinogenic, but it was most favorably used in the past as an NMR solvent because it doesn't contain any hydrogens. And so back in the day, before it was more readily available to make what are called deuterated solvents. So I've mentioned proton NMR before. And so, right, that's how they get a picture of the molecule, except you have to dissolve your molecule in something, and you can't dissolve it in, let's just say, if you were to dissolve it in pure benzene, so that's C6H6, and all you would get for your signal would just be giant benzene, and so you wouldn't be able to see anything. And so they have to, back in the day, they used this solvent. Nowadays, they use deuterated solvents, where you replace the hydrogen with the deuterium, and this is not NMR active. And it's about 99% deuterated for any of these solvents, and you would still get a signal for the 1% of hydrogen contamination, so you'd still see your solvent, but using the deuterated solvents, you can see your compound. So again, that's why carbon tetrachloride was used a lot in the past, but now it's fallen out of favor since it's carcinogenic. And then don't forget your electrons around chlorine, so don't be like me. So draw all your lone pairs. And so when you draw this too, attempt to draw it in 3D, just so we can show, like, yes, it's tetrahedral, because we will encounter square planar compounds in the future. So let's look at ammonia then. Ammonium, excuse me. Make sure you pronounce that. So ammonium. And so when you do your bookkeeping for the electron, now you have to keep or account for this plus charge, and so this means you're going to subtract an electron. So let me at least show you what that looks like, and then you can try to figure out what this looks like. So tally up your total number of electrons. So nitrogen brings 5, each hydrogen brings 1, so 4. But then we have a plus charge. So for my accounting purposes, I'm just putting a plus charge so I know, okay, there's a plus charge on this molecule. And then that means we have to subtract an electron. So I was at 9, now I'm at 8 electrons total. So now see, how would those be arranged? What geometry would it be in?
Does it matter where you take it off of?
No, but what you'll see, so that's where the formal charge comes into play, is when you calculate the formal charge, then you'll see, oh, okay, this is where the positive charge is located. And then that gives you hints about reactivity, too. see some structures. So what do we get for our structure of ammonia? What is it? Ammonium, what does it look like? So nitrogen in the middle, and so stick 4 things on it, probably in a tetrahedral geometry. That makes kind of the most sense. And so now looking at this and doing the formal charges, where is the positive charge located? So on the nitrogen, so if you do it, your formal charge calculation, so 5 minus 4, no electrons on there. So that gives us a 1 plus charge. And so on your structure, you want to draw a little plus charge like that next to the nitrogen. So you're showing, yes, it's located here. And so this also means that nitrogen is reactive. It can take the electrons back. And so what happens with ammonium is if you add it with a base, for example. So our base, let me draw this somewhere else. Let me just redraw it. Because this comes up in lab sometimes. Because NH3 is also equal to ammonium hydroxide, but then you're like, what? That doesn't make sense. And so what happens is if you have a little hydroxide group, so this is hydroxide, just OH with a negative charge on it. So you can see that negative charge is located on the oxygen. And so what it's going to do, it's going to come along. And so this is good skills to start practicing. So the action always, always, always starts at the electrons. And so these electrons are going to initiate. They can pick up this hydrogen. And then because we have this plus charge on that nitrogen, that means that these electrons from our bond will go back to nitrogen. And this means we make water from our hydroxide, and then we reform ammonia. Oh, I didn't draw that in 3D. And so now it has those 2 electrons back on it. Yeah.
How come when you're drawing the, you have like the dashes, or like 3 dashes next to it instead of just doing a single?
Oh, so the wedge, so the wedge means it's coming out of the plane of the board. These dashes mean that it's going behind the plane of the board.
Oh, okay.
And you can draw as many dashes as you need. I just draw 3 by habit, apparently. So yeah, that's all I'm trying to show is the 3D geometry. So let's skip these for now. And let's actually start a new page. Well, let's look at something a little bit more complicated. So let's try this nitrate atom. This is called nitrate. So this is a polyatomic ion, and so this means that it's covalently bonded, has an overall negative charge though. So see if you can figure out what that might look like. And so look at your formal charges too. So do we have ideas yet for the structures? I see some good starts. So how many electrons do we have in this system? I think I heard a 24. So 5 from our nitrogen, 3 times 6 for our oxygen, and then our negative charge. So that gives us an extra electron, so 24 electrons. So that's a good starting point. And so what could we do? We could just start nitrogen, maybe put 1 bond to each oxygen, and then we have to start filling in our electrons. So 1, 2, 3, 4, 5, 6, and then I'm just going to try to satisfy the octet rule until I run out. So 1, 2, 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So kind of what's wrong with this structure?
You don't add the additional electron.
Sorry?
You don't add the additional electron.
Oh, we did with the accounting, right? Because we had 5 from nitrogen, 18 plus oxygen plus the 1. So I have 24 in here. So that includes the negative charge. So there's something funny about this structure.
Yeah.
So you said nitrogen? So nitrogen needs 2 more electrons, so the octet rule isn't satisfied. So that's kind of a problem. So how could we fix it? So double bond. And so let's do that. So that's a good indication. So the other thing you can do is if you were to do the formal charges, so what's the formal charge on each one of these oxygens? So it'd be 6 minus 1, 2, 3, 4, 5, 6 minus 1. That gives you -1. And so you get -1 on all of these since they're all the same. And then what's your nitrogen formal charge? Just from this structure. So +2 is correct, so we have 5 minus 3. And so that's kind of one thing you're checking as well. The structure at least is balanced. So I have a +2 plus -3, so I have my -1 charge. But this isn't very good. You mentioned that nitrogen needs 2 more electrons, so it's octet rule not satisfied. And so kind of the big hint that your formal charge is also telling you is, so if you have a positive charge next to a negative charge, that's not very favorable. And so we can take one of these bonds and let's put them into a double bond like y'all suggested. And I'm just formally moving them too so we can see that these are really all related. And so now we can draw our new structure. Now, did it matter which one of the bonds we made a double bond? So no. And we need to draw that, though, in our structure. So now this is called resonance structures. And so what this is saying is, so it doesn't matter. We can draw all the different structures, and then we want to include our formal charges. So this is a 0. Nitrogen is +1. So negative, negative. So that gives us our structure. And so you probably wouldn't want to make another double bond just because nitrogen can't go hypervalent. And so all that means, and we'll probably continue this next week as well. So this first row, or the second row, cannot go hypervalent. And all that means is we'll see some scenarios where like phosphorus can have formally 10 valence electrons or 12, and sulfur, and they can all do that. And we'll go into why later. Sorry, this is one of my pet peeves. Now I'm just like triggered because your book, I don't remember if your book says it, but so many textbooks are wrong, and they all say, oh, the reason why that the row 2 can't go hypervalent is because they don't have d orbitals, and that's just not true because these are not using d orbitals to go hypervalent, so they can use just their p orbitals, and so we'll probably talk about that later. I just get annoyed with textbooks that say that. But the answer as to why they're not hypervalent is really that they're just too physically small, and so they just can't fit in more around them, and so they can't go hypervalent. So going back to this structure, this is good. But now we want to show that it didn't matter which one we changed, so we want to draw all the resonance structures. So now resonance structures. And so you just want to draw all of them. Drawing in your formal charges. So now rotate it to the last one. Plus, negative, negative. So again, the overall formal charges add up to -1. But then the nice thing about these resonance structures and what it's telling us is it's truly telling us, right, the nature of nitrate. And so the way to think about these resonance structures is if we could combine them all, then our molecule is really an average of all of our best resonance structures. And so looking at all of these, you can see, so this double bond just kind of rotates around, and so if we could quantify this, we say we have 1, 2, 3, 4 bonds over 3. So all of them basically have 4 1/3 bonds, roughly. So, right, they're not quite single, not quite double, so somewhere in the middle, so they're probably going to have a bond length that's a little bit shorter than a normal single bond, but it won't be as short as a true double bond. And then we also can see where the electrons are located. So in all of these structures, right, the nitrogen is always positive. And then we see that this negative charge, so we have, you know, this kind of -2 charge that's floating around. And so all this is telling us is that negative charge is going to be centered around the oxygen. So it's going to be evenly distributed. So again, it's like an average picture of this. So that's kind of the limitation, but also the beauty of these Lewis dot structures. It's like, yes, we have all these little accounting tricks, but it's telling us kind of the true nature of this molecule as long as we average in all the structures. So now, again, this is telling us where the electron density is located, and this is super powerful because otherwise we'd have to plug this into some computational software to get that same picture. All right, any questions on nitrate there? So let's go back and try BF4 in our last minutes of class. So we have Do we have a structure for BF4? So boron in the middle. And that means we can probably put those 4 fluorines around in the tetrahedral configuration. And then where does my formal charge go though? So it has an overall -1 charge, so where is it located? So the boron, so don't forget your formal charge. So anytime you have a charged molecule like this, you have to have a formal charge somewhere in your drawing. And so excellent, so boron is carrying that negative charge. And so that makes sense too. So what do we remember about boron? How many bonds does it typically make? So 3. So it tends to be like boron trifluoride. So that's where it's happy, but then boron, I think I keep saying like people love doing research with boron. That's a really hot area right now with main group chemistry because boron is, they call it, it's a frustrated Lewis pair, and a lot of that is all to do with the fact that it's not satisfied here by the octet rule, but it only has 3 electrons, so now it's carrying a negative charge, and so borons are always super reactive, going back and forth, and you can do fun chemistry with them. So excellent. All right, I think we're out of time. You probably could guess pH 3 from our patterns. So let's take a 10-minute break, and then we'll come back, do our quiz, and then you'll be free to go, and I'll see half of you at 1. So hopefully you got your exam for me. I think I caught everybody that snuck in. Yeah, like all the, like how many electrons are in blah level and like that sort of thing.
No. Gotcha. No, it's only on Thursday. The quantum research, or the quantum looks and like there's electrons, orbitals,
I was doing that, I was starting to draw.
all of the above.
I guess I just don't know.
Yeah, that's not cool. It's chicken a lot. I don't
Started drawing like thousands. What?
So what do we got now?
Chapter
Which is what?
quantum stuff. That's why I'm checking too. That was week 4. It's in week 4. Yeah, it was week 4 stuff.
Oh, that's the midterm review.
Oh, that's you?
What? Week 5 is the midterm review.
Yeah. like what I don't want to happen.
Yeah, that's what I said it was.
No.
Oh, yeah, homework. Oh, yeah, I forgot to hand out homework. Yeah, chapter 6 and 7 are both. Did you all need homework?
I don't.
No? Anyone need homework here? Oh, there's staples still. One homework. Oh, there's 7 staples too.
Oh, okay. We should make sure we do that first.
Oh, you already grabbed it? Okay. Anybody? Don't need
I'm good. No, thank you.
Oh, there's, what time is it?
Oh, it's combined?
That is more for my, like, tracking on how long or the exam is for. Homework? Do you mind, online? No, I don't mind, because I'd rather not. Yeah, it's,
Tried all of them?
the online submission is easy for homework. Did we all make it back from the bathroom? All right, let's do our quiz. It should be easy, I hope. And then, of course, don't forget to put your money as point for extra bonus points. And then have a great Halloween if I don't see you in lab. I'm sure everyone will be partying this weekend.
You'll be working, huh, Joey?
Only if I get all my homework done.
Yeah. So awkward that Halloween is on a Monday. point. Yeah. And then, yeah, you can, cool. Okay. Oh, did you want to put Amelia's point?
Oh,
Oh, thanks.
I forgot to do the money point.
Oh.
You just make it just right on both.
Yeah.
I like your school advice, so sit on the chair.
Oh, wait, you forgot your name?
I did?
Oh, my bad. Thank you. Oh, thank you. Thank you. Thank you. Oh, thank you. Thank you.
How long is the lab today?
Trying to think how long it took people. It's a lot of steps, but they could be done like fast, maybe 2 hours or so.
Okay, I just wondered if I had to pay for more hours.
I don't know. It depends how fast you work.
What was the lab on Tuesday?
It's copper reactions. Are you gonna come to this session?
Can I do it tonight?
Yeah,
What time is it?
1, so same time. Sweet. Yeah, it's a fun lab, so.
Right here? No.
There we go.
Thanks.
Thanks.
Name is Captain.
So I miss a little Tuesday. I don't really remember how to do that. Or if you went over it.
Yeah, we barely did it, so yeah, that's the formula.
So what do we put in the Q's? Is
So
it
they-
like the charges?
Yeah, so the Q's is correspond to the charge, so it would be +1.
And then -1?
Yeah.
And then what's D?
So D is the distance between them, and there's a lot of discrepancies in that value. So what I was telling people in class, I need to post the notes. But for like the chapter 6 notes, there's this chart which tells you like the radius of the ions. So for this one, you'd want to find like fluorine, -1. And so according to this, it's 136 picometers, and that's the radius. And then add that to, so according to this, sodium has a radius of 95. So you could add those two.
What was that, fluorine?
136
So it was 136 and 75?
and 95. But I was trying to find. I had the distance between them. Because the only thing that I was going to add to that is, like, let's say you looked it up. I can't find it right now on Google, but if you just search, like, distance between sodium and fluorine, it might give you a different answer than just the additive answer.
Okay.
So I expect kind of differences in numbers based off of that. But as long as you show your work and I can see, like, okay, you got the distance by adding them, and that's fine.
So is that all we're doing here?
Yeah, and then I think there's a factor missing, because it should be multiplied. My notes would scroll down. I didn't take your quiz. Because the last part of that is 231 attijoules times.
Oh, I missed that.
Yeah, I think there's just a little factor there.
So
And,
before the-
yeah, and that's just a constant. So 231, and then notice the units, so that it gives you attijoules. And it's looking for the distance in picometers, so what I gave you was in picometers, so that's fine. You don't have to convert those numbers of the 135 and the 95. Just again, add them together. Oh, quiz. Yeah.
So it's like this? It's just in front of it, right?
Yep.
Thank you.
Thank you. Is anyone still working on a quiz, by the way? Sweet. No pressure if you were. To detach. So 5 sublevels. Yeah. And then orbitals, that's where you do the 5 squared and. Will he text you if your house is on fire?
Probably now. Okay, so I've questions about, a lot of questions. So for the precipitation reaction, was that when we had the cloudy blue teal and put it on heat?
So before then, so you had the copper, you dissolved it, you made copper nitrate. Then you added the sodium hydroxide, you made that precipitate.
Mm-hmm.
So that was,
That's the decom? Or the, oh, the
Yeah.
precipitation, okay. Is that what so was that?
I thought that was step 2.
I think you're right, yeah, it is, okay. Man. So the other Nikki T gave me a really nice big eraser. I sent her a text last night, I was like, getting a really good workout. Okay, so then,
Yeah, I should have brought my eraser for you. Dusty like gave me an eraser as a present, but it's like, I don't need an eraser. I mean, I appreciate it. I didn't tell that to Dusty.
well, if you need to rehome your eraser, I promise to give it a new home, or a good home. Okay, so then the decomp would have been step 3.
Yeah.
Okay. And then the redox. So I guess what I'm having a hard time with is being able to look at something like this and know.
If it's a redox or not.
Right. And so, like, what am I missing?
So like the biggest red flags for redox, or when you see like a metal is in a compound and then it's by itself. Or like same with like, I think we saw that in, of course I unplugged my computer.
Oh, you had no idea I was going to ask you a bunch of questions about this. So like this
Oh, we haven't
would be a
gone over
redox
that.
where we took the zinc and added it to,
Yeah.
and then we ended up with zinc as part of the compound and copper by itself.
Yeah. And there are like other instances, like if you can do like halogen swapping, so I can't remember like the reaction exactly, but if you had like copper fluoride and then you add iodine to it,
So the iodine and copper fluoride
would swap, so then you would get copper iodide and then make F2, so then that would be your other red flag. It's like, oh, there's some element being made, like something being put into its elemental form and something like starting in the elemental form and going into a compound.
Okay. Okay.
Otherwise, we haven't gone over redox quite yet, but that's just determining oxidation states and seeing if they change in a metal.
I mean, we went over them in biology, but it's kind of a different approach.
You know what I mean? At least I see it as a different approach. Okay, and then with the double replacement reaction, so the cations and anions. So again, I feel like I'm just missing something like flags or some indicator.
So what's the post-last question?
It says in a double replacement reaction, the cations and anions of two different compounds swap partners. So actually, if I just read the question out loud to myself, I probably would be able to. So
So I see one right there, yeah.
So our anion is the copper, and this is
The cation's the copper. So remember, metals are always the cations. You're losing electrons.
okay. Okay.
So yeah, it's like almost always a metal cation.
Was there just one?
I'm trying to remember. I think there's just one.
It says which of the 5 steps? Okay. Okay, cool. I'm trying not to get behind on stuff, so.
And then what was the other step? Because then you had copper oxide and added sulfuric acid to that.
Yeah, so we had a precipitation, a redox, a decomp, a single replacement, and a double replacement. And so,
What about this step though? 'Cause this one is also probably double replacement.
because the H2 is swapping with the copper.
Yeah.
Is that a single replacement though? Because it's only,
It would be a double, because, right, the copper then takes the sulfate.
so what would be the single replacement then?
That was the one at the very end, where you recover out the metal. The zinc plus, zinc plus copper sulfate, so that'd be a single replacement. Since you just swapped one and then made another one. And so single replacements are redox, double replacements are not.
Okay.
Since the single replacement, it's like you start with something in the elemental, then you get something new in its elemental.
Right.
Double, they're just swapping partners, so should not be changing redox.
Cool, awesome, thank you.
You only slightly stressed me out with like the unstapled pages.
I'm stressing you out with my unstable pages? Really? Does that sort of thing stress you out?
Yeah, only because I feel like they'll start flying around and then they'll be out of order and.
Oh, they're definitely out of order. I'll staple them before I give them to you, but I'll make sure they're in the correct order. It's because I printed it when I printed Camille's, and then I just never stapled them. Here, atomic weight is measured, right? It's not exact when it comes to sig-figs. Atomic weight.
What do you mean?
So sulfur has an atomic weight of 32.06. So if we were using that in a calculation, we could only use 4 sig-figs in the answer, right?
Yeah, but.
Oh, it does? Oh, just kidding, I just wrote it down wrong.
Nah. Yeah, and things get fuzzy with the sig figs on numbers, because usually people round oxygen to like 16, but then we don't just chunk it off at 2 sig figs, so.
Makes me,
all the rounding, and it makes me very uncomfortable. I know that there's a really good reason for it that smarter people than I came up with, but it still makes me uncomfortable and makes me feel imprecise sometimes.
Yeah. I mean, ultimately, it just goes back to like what you're doing in lab. Like all these practice problems are more for fun, but then sig figs matter more when you're like trying to measure something and like, can I actually measure this accurately? All that.
Like, to me, it's funny that there would ever be a question about like, should I be more precise? Because I always want to be more precise. Or more accurate or both.
And sounds like you're ready to be an analytical chemist. You sure?
Have you seen my math? Maybe not yet. You're in for a treat.
At least analytical chemists get employed though.
As opposed to,
Well, it depends what you want to do, because analytical chemists, they're the ones that make up most of like the industry, the jobs. But you could also just end up like somebody's bitch as an analytical chemist, just working machines all day. Actually, there's some like documenting on Netflix that's great about how a bunch of drug cases were overturned because like the people doing the drug testing, the chemists were, you know, doing some sampling while they were doing the testing. So then they were not like accurate with their results. So they were crazy high. But that's what happens when you are a chemist in that kind of job where it's just testing samples all day, apparently. Yeah, it was like,
so when I was living in Wyoming, Cody Labs is the name of the company, and I don't know if that is like, I don't know about those industries, so I don't know if that is like a lab that, anyway, there's a lab and they make drugs. And they were hiring for like an over 3 shift, swing shift pill maker, machine person. And I was looking for a job. So I interviewed with the woman, and you can't listen to music, you can't read books, you have to stand at your machine the entire time and just like watch it for 12 hours.
that's awful.
All night. And like, I was like, yeah, I don't think that's a good fit.
Yeah, no music, that's really,
It was obviously a sedentary position where you're just watching your machine to make sure the machine doesn't make any mistakes.
yeah.
And so I can understand if you are doing the same thing every day.
I just can't imagine like not even having music as an escape, like fudge.
Audiobook or something.
Yeah, like come on. That's why people go insane at those jobs.
I think that they actually closed that facility, though. I can't remember why. It was like in an old Walmart.
Yeah, some guy that I knew, he was in like inorganic chemistry, but then he didn't complete his PhD, he just got a master's. Then he went on to industry and his job was literally watching paint dry.
Was he in your PhD program and just didn't finish?
Yeah, he just didn't finish.
Yeah, it sounds awful. But maybe he likes it. Paint is important.
transferring from one thing to another, like that kind of loss?
Yeah,
Okay.
and, you know, you can emphasize whatever you thought maybe you did. Like, I don't know if there's a step that you thought went poorly or better than others. or-
I answered that on the next one.
Okay, yeah.
Hopefully you'll laugh when you hear my answer. I mean, I'm pretty sure I know, like, I'm pretty sure I know what happened for us to end up with almost 165% yield from our original number. I think we just put too much zinc in at the end,
Mhm.
so I don't think it all reacted. Slash, I don't think it could. I think we put too much in. So is NO3 and that's nitrate, right? Is it a nitrate group or is it just called just nitrate?
You could call it like a nitrate group, so it's technically called a polyatomic ion, but, yeah, you could also just say nitrate or.
Sorry, Marissa, I'm gonna ask you all the questions.
That's what I'm here for.
So are you not gonna have, labs split into two groups next time? So just gonna be one,
No, we'll do the same.
same?
Are you gonna have lab on Tuesday and Thursday? Or just Thursday?
Oh, just one day.
Oh.
Or is that what you, sorry,
Yeah.
I misinterpreted.
So, like, are there a whole bunch of people in here that only need to take this class and don't need to do the second and third of the series?
I'm not sure. I know enrollment tends to go down just because people tend to die over the course, but there should not be a huge drop-off, just because I don't know what programs would only want one term. And then what's kind of the other thing is, so if you were to transfer, like, from a quarter university to a semester university, you might be screwed. So you'd want to at least take Chem 221 and 222, so then that would for sure be the first quarter at a semester university. Yeah. So I don't know who would be taking one, but I often find that I think people get bad advice here with advising too, so.
Or no advice, which was the case when I started in the summer. They were just like, cool, you want to take classes, all right. So I didn't know that biology was a three-course series. I
Oh,
had
no.
idea.
Yeah.
And so I started it in the summer. It worked out just fine, but like, it can definitely put you behind if you are unprepared for one of the series.
Yeah. Yeah,
I'm
that,
just about, I have to go back to calculus. I'm just bitter.
not, I'd be bitter too. I'm trying to help other Nikki with calculus, and it's just reminding me like, oh, it's been a while since I did calculus.
Dude, it's been 20 years since I took calculus.
Oof.
So, yeah. So thank you for trying to accommodate class times next term.
Yeah, no, I definitely don't want to put anyone behind a year. Like, I hate that. Like, I almost want to offer, at least this is just me, like, chatting out of my butt. But it's like, I would love to offer a trailing chemistry series to help people catch up, because I feel like I could run it, like, self-taught with all my lecture videos. But between, like, workload and all that, like, I don't know that it would ever happen. Even if I could handle it, there'd be no way to, like, the university wouldn't want to do that, probably, to pay me.
And then would you do the third one during the summer?
Yeah, or what some universities do is they run the entire, all three in the summer, which I would not want to do, but you could, in theory, do. I mean, I could do it.
Like every day for 3 hours? That's
Yeah,
what
or
you're saying?
something like that. I don't know what the schedule would look like. Because it depends how, I've seen a 10-week course compressed into 3 over the summer. So then you take the entire semester over like 9 weeks or 10 weeks, whatever that works out to. I've seen it done for OCHEM.
Oh, God, that sounds awful.
Yeah, I don't recommend it. Like, seeing the students that take it, by the end, they have like zero knowledge. But
And like tired brains. I mean, I was like actually gonna ask what your opinion on doing that is, because any course that I've taken compressed like that, you just end up being really tired at the end.
yeah,
And like feel stressed and feel like you've just been sprinting the whole time, you know?
yeah. I think it's a bad idea. Gen Chem, even though I don't see a lot of universities do it over the summer, I feel like that's sometimes easier than OChem. Like OChem, I don't know how they offer it in the summer. Like, to me, it makes no sense because you have to really take time to like digest OChem, look at it, like see a bunch of examples.
You teach introductory OChem here, right?
Yeah, the Chem 105.
Oh, so it's for, is it for non-majors?
Yeah, because it's just the GOB series, so it just gives you like a little flavor of organic chemistry, but
So you
And-
don't get to teach any of that here,
no, I would love to do OChem here, but
but they don't wanna pay you to do it?
well, right now, given that I'm the only full-time chemistry instructor. But yeah, I don't know what it would take to develop an OChem class. We'd also need more equipment, like you at least need some rotovap, some more fancy stuff, and more toxic chemicals, fume hoods. So, I mean, we do have 2 fume hoods in each classroom though, so if it was a small OChem class, you could maybe make it work.
I can't see that many people here wanting to take OChem or having, well, I feel like if it was offered, people would take it.
That's how I feel, because then everyone goes to SOU to take OChem, but
I mean, the reason that I am not taking these classes at SOU is because it is as much money for one term at SOU as it was for all 3 terms here.
geez.
Because you have to, if you take one class, you still have to pay all the fees, and the fees are like $500. You know, the like gym fee and the lunchroom fee and the $500 fee, like, for things I'm not gonna use, you know, but you have to pay them regardless of how many credits you're taking, and so, because I was gonna do, I think we were, I was looking at taking all of my classes at SOU this year, and financially, it just doesn't work. This is also closer to home, less driving.
Yeah.
Thank you for answering all of my questions. I think I did ask you all of my questions.
Okay, like, can you talk about the redox? Like, how to identify a oh, never mind. Okay, thank you for just letting me talk that out. So a reaction can be both a single replacement and a redox reaction, right? You said that
Yeah.
redox are often single replacements, but never double replacements.
Yeah.
Full hour before everybody else. So there was a group of people that left our physics exam yesterday a full hour before everybody else.
Wow.
You know, it was like a couple of people finished and left, and then everybody else was still there a full hour later. And I just,
Oh, man.
I'm just so curious. Like, have you had it before? Did you just leave half of it blank? Like, just so curious.
I always wondered that too. Of course, Dusty could tell us as a professor.
Right, well. And now you're on the other side of it, so now you know why people are leaving an hour before everybody else.
Yeah.
But
It can always be a combination. Like sometimes you have that one student that aces through it, but I've also seen where like a student rushes through, they think they did perfect and they're the first one done, you know, before everybody, but it's like, oh, you probably should have slowed down and.
extra work. Like 4 or 5 times.
Yeah. Or yeah, they left half the exam blank and that's why they're rushing out.
I mean, it was not, I think that it was like an appropriately difficult exam. It took most people between an hour and 45 minutes and 2 hours. So, but Oh, so on the spectrophotometer lab, my question about the lab was like, what would happen if you put sulfuric acid, for example, just as an example, or like just a different clear compound into one of those machines? Would there be a result? Because we were, no, okay, because it's clear, so it's
Yeah.
not reflecting or absorbing, okay. I have a lot of questions about stuff. You should have met me as a kid. It was terrible. I would like ask questions to just strangers like in the grocery store.
Nice. That's good.
Not if you were my parent, though.
Yeah.
Scary if you were my parent. I think this might have been my favorite lab so far.
Yeah, it's definitely, I think, one of my favorites.
I have a weird question. So would mercury and lead have the same amount of core electrons?
Sorry, I'm not staring at a picture.
Sorry. I'm a little, I'm kind of catching up here, but, so the valence, none of the d orbitals count, right, for valence, it's just, the s and the, e orbitals, but then, so like lead, you got your 2, and then 2 here, and then e, but you subtract the valence from the, amount of, the atomic number, right?
So the valence electrons just follow like the group.
Okay.
So like lead has 4 valence electrons, but then the oddity is all these, because there's like different ways to count them.
Yeah.
So usually, in reality, they go by this number, and that's not quite reflected in the electron configurations that we've been doing in class, because like this one is 4s2, 3d1,
Yeah.
but then it really just behaves like it has 3 valence electrons, and generally those are in the d. So
So,
then mercury should have 12 valence electrons.
I wondered if you could hear me yelling at Camila.
okay, so it kind of counts
Here.
a little bit, so 12, because you got your 2 here, and then your 10.
Yeah.
Okay. I was just
Those
confused
are
about
only
that.
for like the transition, so that's why I don't ever ask like how many valence electrons the transition doesn't have. Like that's more confusing, and that would be for like inorganic chemistry and other separate course.
Yeah, I was just curious, because, the core electrons for lead would just be 78, but would it still be the same for mercury? Because I was thinking the way is you subtract the valence from the
Oh, yeah.
core.
Yeah, you're right, so they have the same core amount, because their core is like xenon.
Xenon?
Yeah, so it goes like 54 in the core, and then.
Okay, I don't know, I was just thinking, so, all right, cool, thank you.
I need to migrate soon.
I'm gonna start watching for a secondhand cart for you. I'm gonna like roll in one day, like a buggy cart. The problem is that when you have carts like that, then you just start putting all of your shit
Yeah.
on there, and then you just end up with a cart full of.
I know, I do need a cart, apparently. I didn't bring my backpack for some reason.
Oh no.
I mean, it's in my office, I just.
You need a hand cart.
I'll probably be